last time we did refraction, this time we are on to reflection. And because it's pretty short what I have to say about reflection, I'm just going to throw in a little bit about intensity as well, which is going to be another little short snippet. Now, I'm going to assume that we all remember the law of reflection, that the angle of incidence is equal to the angle of reflection. That, you know, it just comes in at the same angle it goes out. So I'm just going to talk a little bit about total internal reflection real quickly. Again, this should just be a recap from GCSE, but I want to make sure it's clear in your mind. So, total internal reflection only happens when I have a light ray that's incident on a boundary where material 1 has a higher n value than material 2. So n2 has to be less than n1 for total internal reflection to be a possibility. Okay, that's the only time it can happen. The other limitation on when it happens is that the angle of incidence has to be greater than the critical angle for this boundary, this interface. So the critical angle depends on what material you're in and what material you would be going to. So for total internal reflection, I need to be going from something that is more dense to something that is less dense, and I need to be greater than the critical angle for that interface. So let's just have a little look at what we mean by the critical angle. So the critical angle is the angle at which, if I sent this, that the light would actually be refracted at 90 degrees. So it would give me an angle of refraction of 90 degrees. So if I used n sine theta 1 equals n2 sine theta 2, that would give me n1 times sine of this critical angle is equal to n2 times sine of 90. Now sine of 90 is equal to 1, so that gives me n1 times sine c equals n2. So sine c equals n2 over n1. So basically, that's where it all comes from. You can see it. Those of you going for the higher grades will need to be able to show where it comes from. The rest of you just need to be able to use it. So what this is saying is that if I want to find the critical angle for an interface between two materials, I do n2 divided by n1, and that will give me the sine of the critical angle. So I can find out what the critical angle for that interface is. And if we're travelling into air, just a little note, I obviously forgot, so it's why I put it in the box. If you're just travelling into air, that's going to give me sine c equals 1 over n, because remember that we said that the refractive index for air is always taken as 1. So you just do 1 over the n value for the other material, and that will give you sine c anyway. Okay, so that's pretty much all the theory for it, all the mathematical theory, sorry. We just need to talk about when it's used. So hopefully I say total internal reflection and you instantly go, oh, we use that in optical fibres, and that is where it is mostly used. We use something called step index optical fibres, and basically, in a real simple sense, they consist of 2 layers. So the core and then the cladding. Both are transparent, but they are slightly different materials, so have different n values. And the core is the one that has the higher refractive index than the outer layer, so that means that the total internal reflection can happen within the core. Okay, so like I said, it takes place at the core cladding boundary, and the reason we have the cladding layer is it prevents light from sort of crossing between fibres. If I've got like big bundles of fibres all together, then I don't get light travelling from, you know, like the cable from the stock exchange doesn't want to get mixed up with the cable from the greengrocers. You need to make sure that the data stays separate, and that cladding allows that to happen. Okay, yeah, because that leads to insecurity. So optical fibres, basically we just send pulses of light, they go from one end to the other, and that's pretty much the deal with optical fibres. I'm sure you know that. So we've got the idea that we've got the core and the cladding. We've also got this thing called multipath dispersion. I'm just talking about this just in case. I don't think it's likely to come up, but hey, I'd rather you knew more than you needed to than not enough. So multipath dispersion is caused when your core is too broad. And if your core is too wide, there are lots of options that light can take where it can still travel all the way along the core without leaving it. So for instance, I've got the red line there, which is where it just goes straight along it. Then we've got the green line where it's, say, travelling just above the critical angle. So it's only just staying in. So those are your two extremes. Now when I first put them in, my pulse might have been all nice and close together and collected and just real short. But because the red one arrives, and it's about the size that it originally was when it started, but the green one takes longer to get there. It stretches out the pulse, so I end up with a different shaped signal at the end. And basically, that it just happens because of the big path difference. And a way to prevent this is to make the core a lot smaller, because that means that there are less angle options at which the light could be hitting. Sorry, that's not quite what I meant. Because with the angle options, there are less path choices that would be acceptable, that would let it still travel along. So there isn't a big path difference between the longest and shortest possible path. Okay, yeah, so basically it just changes the signal, so you end up with a bit of distortion. So as well as optical fibres, another use of total internal reflection, it's inside endoscopes. Basically, again, the bundle of fibres, and one transmits light and one sends it back. And they're useful for all sorts of things, including getting toys stuck out from inside of noses. Okay, that's total internal reflection. So I'm just going to do a real quick whiz through intensity. Intensity is basically going to really boil down to two equations that you just need to know and use. You need a bit of a definition of it. I'll try and explain where the second one comes from, but if you don't get it, I'll just point out the bit you just need to remember. So, intensity is power per area. So it's how much energy is transferred per second per unit area. So if you sat somewhere and the intensity of the sun is really high, it means that in that area there's a lot of energy being transmitted to you per second. So it probably feels really warm. So there's the equation, I equals power over area. The unit for intensity is watts per metre squared. Power is in watts, area is in metres squared. And then that's pretty much the basics of it. Just some little extras. The further away you get from a source of waves, the lower the intensity will be. And that's because that energy, that power, is being spread over a larger area the further away you get. And because the energy, that power, is being spread out in every direction all at once, that means that the area over which that energy is being spread is actually spherical. So if we then looked at that area, put it into the equation, it would give me that the area now becomes pi r squared. So we have what we call an inverse square rule for intensity. So as I go away, the intensity doesn't drop linearly with the distance away I am. It gives me a inverse square, so it drops off quite rapidly. So just think of a squared graph, and you'll get the idea of the shape. We're going to meet a lot of inverse square rules next year, so this is just starting you off on that front. Don't stress about it too much right now. It could pop up as an extension type question, so it's worth just having it in mind. Right, the other thing we need to know about intensity is how it's related to amplitude. So intensity tells us about how much energy there is. If there's less energy, it means the particles are moving slower. If particles are moving slower, that means the amplitude of the wave will be smaller because they've got the same time to do the number of oscillations, so they're not going to travel as far, so the amplitude gets smaller. So if I start with saying intensity is proportional to energy, well, that makes sense, we should be fine with that. And the energy, the kinetic energy, is proportional to v squared, because kinetic energy equals half mv squared. And the speed, v, is proportional to the amplitude. Now if I combine those three things together, it gives me a relationship between intensity and amplitude. And it tells me that intensity is proportional to amplitude squared. If you can follow this thought process through, fantastic. We are going to look at playing with a lot of proportional relationships. If you can't quite follow it, you're not totally happy, don't agonise at this point. We'll come back to these sorts of things over and over. But you do need to take away this equation, that intensity is proportional to amplitude squared. Okay, so that is refraction and intensity, and we will do a whole load of practice in class. So remember, any questions? Ask when you see me.